Okay, let's start with the contents first. First, I will explain about the wavelet transform theory, that how you can take the wavelet transform of images using filter banks. Then I will explain you about the Anaconda and Spyder for Python code development. And then I will explain the Python package, which is a PyWavelet, that is responsible for doing all the wavelet transform analysis. And then I will explain you the two important functions. One is the DWT2 and IDWT2 for taking the wavelet transform of images. And then I will show you one example of Python code for this. And then I will explain the WebDec2 and WebRec2 Python functions with the Python example code. Before watching this video, I recommend you to watch my previous these three videos. The first one is about the wavelet transform theory and its application. The first one explains about the theoretical aspects of the wavelets, that what are the wavelets, what is the filter banks theory, and what are the different applications of the wavelet. Okay, and the second one is about the images, specifically that how we take the wavelet transform of images using MATLAB and Simulink. And the third one is about the Python, so how you can do the wavelet transform analysis of 1D. So I have covered the audio signals in this video, so you can refer this video also. So I really recommend to watch these videos for better understanding of this current video. Now let's see that how we can get the wavelet decomposition of images using filter banks theory. Okay, so here you have one image of size m by m, and then using the low pass decomposition filters and high pass decomposition filters, we can get the wavelet coefficients. For that, we need to do the row wise and column wise operations on images. So first we pass the image through the low pass decomposition filters, and then high pass decomposition filters, and then downsampling by 2. And then we pass the output through the again the low pass and high pass decomposition filters, and then doing the downsampling by 2. And by this we get all the 4 matrices which represent the wavelet coefficients. The first one is known as approximation coefficient, the second one is known as the horizontal detailed coefficient, and the third is the vertical detailed coefficients, and the fourth one is known as the diagonal detailed coefficients. The approximation coefficient matrix actually includes all the low frequency detail of image, while all the detail, I mean the horizontal, vertical and diagonal detail coefficient matrix, they includes the high frequency detail of your image. That means particularly the edges. Okay, and let's see that what happens to the size because of the downsampling. So if you have the image of size m by m, then because of the downsampling you get all these 4 matrices of the half size, that is m by 2 m by 2. So for image of 256 by 256, the size of these 4 matrices will be the 128 by 128. Now let us see the reconstruction, that's the inverse wavelet transform. So we have all these 4 matrices, CA, CH, CU and CD, then doing the reverse operation, that means upsampling, and then passing through the low pass and high pass filters, and again doing the column wise and row wise operation. Here the filters are different than the filters used in the decomposition. So here the filters are reconstruction filters, and in the previous decomposition they were the decomposition filters, so their impulse response are different. And then at the output of this reconstruction we get our image back of the same size. Okay, This is one example. Very clearly you can get the idea that what happens when we do the one level decomposition of image. So you have an image of size, let's say m by m. Then after one level of decomposition, your discrete wavelet transform, you get four matrices. As I said in the previous slide, CA, CH, CV, and CD. And CA, obviously the approximation coefficient matrix. This is horizontal matrix. This is vertical detail coefficient matrix, and this is diagonal detail coefficient matrix. And because of the downsampling, their size is reduced to the half of the image, that is m by 2 by m by 2. This approximation coefficient matrix obviously will include all the low frequency detail of the image, while this horizontal detail coefficient matrix will include mostly the horizontal edges, and the vertical detail coefficient matrix will include the prominent edges which are vertical in nature, and this diagonal matrix will highlight all those diagonal edges. And if you want to do further decomposition, let's say level 2 decomposition, for level 2 decomposition you have to take this CA1 matrix again. So the CA1 matrix will be decomposed in the similar way. So as you can see that CA1 matrix is further decomposed in a similar manner to all those four matrices, and our size will be reduced further by m by 4 and m by 4. Okay, and if you want to go for the third level decomposition, then again CA2 will be decomposed further in these four matrices. So you can do the multi-level decomposition. Here one example image you can see of size 256 by 256. This image I have drawn purposely in such a way that it includes a horizontal, vertical, and then a diagonal edges. So let's see the strength of wavelet. After the one level of decomposition, we get these four coefficient matrices. So this is CA1, this is CH1, this is CV1, and this is CD1. So you can see that in CH1 that all horizontal details or edges are highlighted. So these coefficients are bigger in the magnitude, and in vertical, I mean CV1, all vertical edges are highlighted, while in CD1 all the diagonal edges are highlighted. So that is the strength of wavelet transform, which has the capability to capture the edges in these directions. So that's why the wavelets are very popular in the pattern recognitions, I mean the feature extraction for various types of input images. And this is the second level decomposition. So your CA1 matrix is further decomposed into four matrices. Okay, so here you can see that horizontal, vertical, and diagonal edges are more prominent at the second level. And here one example of a natural image of Lena. So this is the level 1 decomposition. You can see all those four matrices. That means your approximation CA1, CH1, this is CV1, and this is CD1. So in CV1 you can clearly see that this vertical edges, you can clearly see the prominence of these vertical edges in CV1, while these are completely missing in horizontal and diagonal coefficient matrices. And similarly, you can see that, for example, that this lip line, which is horizontal, this is more prominent in horizontal coefficients, while this is completely missing in vertical and diagonal. So that's the beauty of wavelet transform. And this is the second level decomposition of image, and this is the third level decomposition of the image. Now let's see the Python development environment. I recommend you to use Anaconda distribution for Python code development. Otherwise, you have many choices of different IDEs where you can develop your code. The Anaconda is a package manager, and one good thing is it is free and very easy to install, and it offers a community support also. And with over 19 million users worldwide, it is a industry standard actually for development, testing, and training. You can download Anaconda from this link. The link is given in the description also, or you can search in the Google search. It is very rich in packages. It has more than 7,500 packages. It includes the Jupyter, Spyder, NumPy, Pandas, Numbers, SciPy, and TensorFlow, Matplotlib, etc. All popular packages to develop your codes. And the IDE, the Spyder IDE is included in this Anaconda package. So I really recommend this Spyder IDE for those people who are writing their codes in the MATLAB environment, because the Spyder IDE's GUI is very similar to the MATLAB. So for the people, those who are using MATLAB, it will be very easy for them to migrate to the Python in Spyder. And now this is the PyWavelet Python package that will be used to actually the Wavelet Transform. So it's open source, and it combines the high level interface with the low level C and Python performance. And one good thing is that it comes with the Anaconda distribution, so there is no need to install it separately. And its dependencies are NumPy, SciPy, and Matplotlib. So again, all these three come with Anaconda. So again, there is no need to install them separately. And I recommend you to go to the documentation of the PyWavelet on this website. So this link is given in the description, or you can search in the Google. Now let's see the Wavelet Transform, that how we can do the Wavelet Transform of images using the two functions. The DWT, it is decomposition, and IDWT2 is a reconstruction function. So this is the general syntax. This is for decomposition or discrete Wavelet transform, you can say, and this is the inverse transform. So here the C is your output, and this is your function PyWT.dwt2. X is your input image. W name is the name of the wavelet that you are using. For example, if you are using the HAR wavelet, you need to write the syntax HAAR in these quotes. And then mode equal to the extension mode. The extension mode is actually known as a signal extension mode to deal the boundary problems. Here you write one string, for example, such as symmetric, periodization, etc. I recommend you to use periodization always, okay, for your general projects. And then axis, this is optional and no need to write it. It tells that axis over which we compute the DWT. So let's see one Python code which utilizes the DWT and IDWT2. Okay, so you need to import some libraries, and then you are reading your image. So w256a.bmp is my image that is residing in the current directory. With that I am read function, and then executing the pywt.dwt function as I explained syntax. This is my image, this is the wavelet db3, Davishi's 3, and the signal extension mode is the periodization. So I get the output coef2. This is a variable which includes the tuples. That means it includes all the coefficient matrices. I'm in the CA, CH, CV, and CD. And this is the image reconstruction using IDWT. So all coefficients are passed here, and then db3, and then signal extension mode, and you get your signal back. I mean your image back, but it is in format double, so I am just converting into unsigned integer 8 for display purpose. And these are some plotting commands defining the output figure size is 30 by 30, using subplots to plot all those four matrices actually. So this is approximation coefficient matrix, and the color map I am using is the gray. Okay, and this is the title, and the font size of the title is the 30. And this is the plot of your horizontal coefficient. This is the plot of your vertical coefficient matrix, and this is plot of your diagonal coefficient matrix. And then this is the separate plot of your reconstructed image. So let's see what happens when I execute this program in Python. So let me jump to the Python. I'm in the Spyder IDE. So where's the Spyder? This is my Spyder IDE. So this is my program, which I have already written to save the time. Okay, so I'm just pressing this run button. Okay, so this is executed, and this is what I'm getting here. So this is my output. This was my image, and this is the approximation coefficient matrix. This is horizontal coefficient matrix. This is vertical coefficient matrix, and this is diagonal coefficient matrix. So you can clearly see that all horizontal edges are highlighted here, all vertical edges are highlighted here, and the diagonal edges are highlighted here. And this is the reconstructed image. I can copy this image to my MS Paint, for example. Let me open the MS Paint. So I can see the enlarged version here. I can see more clearly. So this is my horizontal coefficient matrix, this is vertical coefficient matrix, and this is diagonal coefficient matrix. Okay, so let me jump to my presentation. Okay, now let me explain the Wavelet 2 and Wavelet 2. Actually, these are the multi-level wavelet decomposition and reconstruction. In the previous functions DWT, actually they were the single level decomposition. So suppose you want to do a 3-level decomposition of an image, then you have to execute those DWT functions 3 times. So to avoid this, these function, I mean the Wavelet 2 will be executed once to do any level decomposition, and that means the nth level decomposition of an image. So let's see the syntax. So this is the syntax of wavelet decomposition. This is the syntax of reconstruction. So it is similar to the previous DWT. So this is my name of the function, X is my image, and W name is the name of wavelet. Use in signal extension mode, again the similar, where you will write symmetric, periodization, etc. to deal the boundary problems. And then label, here you will write the decomposition labels. So if you want a 3 decomposition labels, so you will write label equal to 3. Okay, and then this is your optional access command. And for label, if you don't define any label, the function will take the default value as a max label. The max label is actually given by this formula, which is computed as data length. That means the size of image, and divided by the filter length. Filter means the wavelet filters length minus 1, and then log 2 of it. The wavelet filter length actually depends on the type of wavelet which you are using. Now let's see the this output C variable. This is need to be explained. All the wavelet coefficients are actually accommodated by this C in the form of tuple. So you can see this is how the all wavelet coefficients are actually taken by this variable C. So the first matrix is CAN, that means at label n, the approximation coefficient matrix is the first matrix. And then second matrix, actually this is known as the tuple. So the first tuple is showing the all wavelet coefficients at nth level, or detailed coefficients, and then next tuple includes all the wavelet detailed coefficients at n minus 1th level, and in the last this tuple includes all the wavelet detailed coefficients at level 1. So in the next slide I will show you that how you can extract any of these matrices from the variable C. So this is how we can access the wavelet coefficients. So for example, let's say I'm doing a 3 level of decomposition using Wavelet 2. So I will get C output like this. So the first matrix is the CA3, which is the approximation coefficient at level 3. And the first tuple is all detail coefficient at level 3. And the next tuple includes all the detail coefficients at level 2. And the last tuple include all the wavelet detail coefficients at level 1. So if you want to extract this CA3, you can do like this always. So with the C0, you can take out CA3. Similarly, if you want to take out this CS3, CV3 and CD3 tuple, you can use C minus 3. And for next tuple, you will use C minus 2. And for the last tuple, you will use C minus 1. Okay, so it is quite easy. So let's see one Python code which will utilize the Wavelet 2 and Wavelet 2. Here we import some libraries that will be used, and then reading the image, and then executing this Wavelet 2 for Wavelet Transform. This is our image. DB5, the wavelet which I am using. Then signal extension mode is the periodization, and I'm doing the 2-level decomposition. Okay, and here this is the reconstruction. I'm in inverse Wavelet Transform by the Wavelet 2. So whatever coefficient C I'm getting, the same I'm passing here with the same wavelet, same signal extension. So I'm getting the IMGR, which is my reconstructed image. It is in the form of double, so I'm for display purpose, I am converting this into unsigned integer, because in original it was in unsigned integer 8 mode. And this is how I am extracting the coefficient. As I explained in the previous slide, the approximation coefficient at the level CA2 will be extracted by C0, because since it is a 2-level decomposition, so C equal to CA2, and then CH2, CV2, CD2, one tuple, and the next tuple is CH1, CV2 and CD1. So this is taken out by C0, and then this is taken out by C minus 2, and this is taken out by C minus 1, as you can see here. Okay, so you can take out all these coefficient matrices, and I'm plotting all the coefficient matrix at level 2. I'm plotting all these 4. So let's see what are the plotting commands. The output figure size is 20 by 20, and I'm using the subplot. So first I'm plotting the approximation coefficient at level 2, CA2, with the color map of type gray. And then I'm plotting the horizontal coefficients, and then plotting vertical coefficients, and then plotting diagonal detail coefficients, okay, at level 2. This is something different command, PYWT coefs to array, which I have not explained. Let me explain here. Actually, this command will extract all the wavelet coefficients and put them side by side to make this type of representation, as I shown you in my earlier slides. So at the level 2, or as I'm doing the 2-level decomposition, so the all matrices will be in this arrangement. So this is your CH1, sorry, CV1, and this is CH1, this is CD1. So diagonal, horizontal, diagonal and vertical detail coefficients at level 1, and then at level 2 your this is your CA2, this is your CH2, this is CV2, and this is CD2. So all these matrices will be arranged like this. It is just for representation. So I am plotting a separate figure to show all the wavelet coefficients in this arrangement. So you will be able to see when I will execute this program. And here the plotting of reconstructed image. So let me jump to the Python. So let me open the Spyder. this program I have already written to save the time. So let me execute this by pressing this button. Okay, it's done. So this is my reconstructed image, and these are the coefficients at level 2. So this is approximation coefficient at level 2, horizontal coefficient matrix at level 2, and this is vertical coefficient matrix at level 2, and this is diagonal coefficient matrix at level 2. Now this was the output which I was talking about. Okay, I mean this command when I was talking about the pywt.coefs2 array. So I'm extracting all the coefficient from this output C and putting them side by side in this representation. So this matrix is CH1, this matrix is CV1, and this is your diagonal matrices. So this is actually all the matrices are put in side by side to see all the coefficient matrix at one place. Okay, so let me jump to my presentation. So this is all about this video. Thank you.